I'm David.
I'm Tyler.
And this is Nuclear Chemistry.
What is a nucleus, you may ask? A nucleus is a positively charged core made up of protons and neutrons. Most nuclei are not very stable and give off different particles to stabilize. To be the most stable, nucleuses have a proton to neutron ratio of 1 to 1 or 1 to 1.5. When nucleus try to stabilize, they give off different particles. So the first particle here that's given off is the alpha particle, which is a helium atom given off as a ray. And next is the beta particles, which is an electron given off by radioactive decay. The third particle is a gamma ray, which are highly electromagnetic radiation, also given off by radioactive decay. Okay, the next part of stabilization is electron capture, where a nucleus absorbs its own electron and gives off a neutrino. Each of these three different particles have different penetrating strength. So first off, an alpha particle can go through a sheet of paper. Next, the beta particle, which can go through pieces of lead, it's pretty strong. And thirdly, but not lastly, but lastly, is the gamma ray, which can go through concrete, which is a lot stronger than the rest of them. Gamma rays are also very deadly to humans. Thank you.
Today we are going to see which radiation is stronger, the gamma ray or the alpha ray. Up first we have the gamma ray. Up next we have the alpha ray. As you can see, the gamma ray is stronger.
When looking at the neutron ratios of all the elements, an interesting pattern emerges. When you look here, which is a graph called a band of stability, you can see that as the atomic number increases, the number of neutrons also increases. Okay, you can see it doesn't follow an extremely linear style, as it kind of follows an exponential form as the atomic number increases. Okay, you also seem to notice that as it stops right here, and that is because it reaches atomic number 83, which is bismuth, and you know then that all atomic numbers above 83, which is bismuth, becomes unstable. Now, that's why that'll stop there. There's no more stable ratios above 83.
Hi elements, how are you doing today?
Oh, I'm doing pretty good.
I have so much energy!
Well, as you can see here, chlorine is a very stable element under the atomic number of 83, whereas mendelevium is an unstable element over the atomic number of 83.
Energy is mass. Here's why. A while ago, scientists tried to figure out the mass of an atom by adding up the mass of the electrons, the mass of the protons, and the mass of the neutrons. Now, when they added up these numbers, they found out that the mass they calculated was different from the actual mass that the atom weighed. Now, no one could figure out why this was, what they were losing, or why. So, this brave man, and his name was Albert Einstein, he came up with an equation to explain this phenomenon. Now, his equation is E equals mc squared. E being energy, m being mass, and c being the speed of light squared. Now, this equation is extremely special because it shows that all energy is directly related to all mass and vice versa. So basically, if you have enough energy, you can turn anything into mass, and if you have enough mass, you can just change it directly into energy. The possibilities are endless. Let there be change! No! Stop the video.
A particle accelerator is a device that accelerates stable or unstable particles straight into a nucleus in an attempt to create enormous amounts of energy, create new isotopes, and to also study nuclear physics. This right here is an example of a particle accelerator. This is the nucleus, and this is a proton that accelerates all the way around a 5 mile diameter straight into a nucleus. The fastest particle accelerator at the Fermi National Accelerator Laboratory accelerates protons to approximately 185,994 miles per hour, which is also about 6 miles per hour off the speed of light, or as fast as I run my 800.
False.
With Einstein's theory of relativity, nothing can ever reach the speed of light unless it is light itself. Therefore, we will never get this poor proton 6 miles per hour faster.
In today's race, we will have the speed of light versus other particles.
Speed.
3, 2, 1, go! As you can see, by Einstein's theory of relativity, no other particle can reach the speed of light.
Did you know that every radioactive material is constantly trying to make itself more stable? Now, this can be shown in the equation here for half-life. Now, this equation shows that the final mass of a radioactive material equals its initial mass times 1/2 its half-life, which is n. And its half-life is the amount of time it takes for a radioactive material to halve its mass. This equation is directly represented by a graph here, which shows that for any given time the mass is constantly decreasing. Now, if n is its half-life, it starts here, it gets to half, and it constantly halves itself indefinitely, as shown here by the graph. Now, in reality, this equation shows that the mass would never actually reach 0, but in reality, it would reach 0 because the radioactive material would eventually just become stable. But this graph is still extremely useful, and we use it to use research on most things. Now, one of the most important things about the half-life is because we can use it to do this thing called carbon dating. Now, this is carbon-14, which has a half-life of 5,730 years. Now, this is extremely useful because we can use it on ancient dinosaur fossils. We can find the amount of carbon left in it and determine how long ago things like the dinosaurs lived. Out front. I got a half-life of 10 minutes. How about you?
I have a half-life of 2 seconds.
I should have said rip. We can do it.
There are 2 main ways to generate huge amount of energy from atoms: nuclear fusion and nuclear fission. Nuclear fusion is where elements combine to make one larger mass. The sun is a great example of this because it fuses 620 million metric tons of hydrogen to helium every single second. Every 4 hydrogen atoms that combine releases 27 million electric volts, which is just an example of the enormous amounts of energy that fusion creates. The next way that creates huge amounts of energy is fission. This one splits atoms and creates two smaller masses. A good example of this is the atomic bomb, which creates huge amounts of energy, which creates a chain reaction because it's uncontrolled and blows up everything. Today, we'll be testing a new device that creates a chain reaction due to nuclear fission.
Hey, buddy.
Do